And we do have a session after class in the library. I didn't put it up here for if anybody's interested. So that's still because it's Wednesday, although it feels like Monday. And so I have us starting right about when my computer's kind of catches up, right about here. We're starting on our second titration problem in part 8. So tomorrow you guys are doing titrations. So I call them titrations, but actually so far they're just aqueous solution stoichiometric problems. Oh, come on, dude. Go. No, now it really got mad. Oh, yeah. I forgot. So here's a build here. So I brought some extra one of these. So which lab are we doing tomorrow?
Lab 8.
Lab 8. And I know Joshua stopped by my office because he was like, no, what lab are we doing? Now, anybody want an extra copy of this? I found mine. You found yours? Okay. Because I started to think, did I really? Okay. And while I'm back here, I see some homework. Take yours. Homework? No? Okay. Homework? Okay. Any takers?
I actually have a question on this one. Wait till the.
Okay. Okay. So there we go. Okay, now it's working. Voila! This should be like the second problem in this part 8. And then we're going to loop back around and pick up part 2 and 3. So what I said is I usually take those numbers and I put them under the species they're talking about. So let's do that right quick. So what is the concentration of H2SO4? So find H2SO4, question mark M. If we have, if 25 milliliters of the solution, it must be that 25.0 milliliters, that must be H2SO4 too. So 25.0 milliliters required. And then we have two things about the NaOH. We have 27.7 milliliters and we have 0.444 molar. Okay, so one of the things I told you yesterday, or when we met on Monday, is I focus on the thing I know most about. And so actually you're going to see on a series of slides, we're going to start with the NaOH, so we can use molarity and volume to get to moles of NaOH. And then the next thing is we can get to moles of H2SO4 using stoichiometry. Okay, and then once we have moles of H2SO4, we can just take that moles and divide it by volume to get molarity. So moles divided by volume, which was given, will give us molarity of H2SO4. So that's the plan. That is the game plan. So when you do these for your test or for homework, I would suggest you kind of label what you're doing, kind of communicate to yourself and to me. So this is titled moles of NaOH in that volume and that molarity. So you can start with either term, but I usually start with the volume, 27.7 milliliters over 1. And then I have to get it to liters, and I can do that by taking 1 liter over 1,000 milliliters. And then I'm ready to plug in the molarity, and I want liters to cancel, be left with units of moles. So what? That's 0.444 moles of NaOH over 1 liter. So now it's quite likely that if I put that blue title there for this in my calculation, I may not even say NaOH in this. I might just leave it kind of just nondescript because my title said it was NaOH. Looks like round to 3 significant figures. I got 0.0123 moles of NaOH. So that's step 1. We use the volume and molarity to get to moles. Then step 2 in our strategy, was to get to moles of H2SO4 using the stoichiometry. And we happen to have kind of a little more interesting stoichiometry. We have 2 moles of NaOH for every 1 mole of H2SO4. So I want moles of, so I'm going to piggyback. My first term is going to be the moles of NaOH I found before, 0.0123 moles NaOH over 1. Now here I do have to say moles NaOH. If I don't say moles NaOH, this ratio I'm going to put doesn't make sense. So I want moles of NaOH to cancel, so I'll put 2 moles of NaOH on the bottom and 1 mole H2SO4 on top. All right. Looks like we still need to round to 3 significant figures, and I got 0.00615, and that would be moles of H2SO4. So that was the second of 3 steps. Now what we're after is molarity, so we can take those moles and divide it by the volume of H2SO4. And it looks like this. The volume in the original problem was 25.0 milliliters, so we have that 0.00615 moles H2SO4 over 25.0 milliliters. Now that will give us moles per milliliter, but we want moles per liter. So we need to get liters on the bottom, so it looks like if we go with 1,000 milliliters over 1 liter, that will happen. Round to 3 significant figures again. And that will be our answer. I got 0.246 moles H2SO4 over 1 liter of solution, or simply 0.246 molar H2SO4. Okay. So aqueous solution stoichiometry calculations. I have one more. And it looks like this. Now this one is a little bit different. Let's kind of put underneath the stuff what we know about and what we're after. Okay. It says, what is the concentration of Na2SO4? So that's a product. So question mark molarity. Okay. And then it gives this information that we just worked with before. It says, what is that molarity if you had 25.0 milliliters of H2SO4 and 27.7 milliliters of NaOH at a molarity of 0.444. You're like, really? Okay. So we're after molarity. So molarity is moles divided by volume. Okay. So do you guys buy this, that we can get to moles if we just take we can get to moles of, I'll write it down. 1, the moles of NaOH. We just did that. Moles of NaOH. That will feel very familiar. That was that 0.0123 moles. Moles of NaOH using volume and molarity. And then we can get to moles of Na2SO4 using stoichiometry. Looks like we've got, what, a 2-to-1 relationship from the balanced equation. So we can get to moles of moles of Na2SO4. Then we have to divide that by volume. So here's the catch. What volume are we going to divide it by?
The 27.7 plus 25.
Exactly. You got it. That is going to be our total volume. That's it. It's like juicing it up and creating that product over there. And what it's swimming around in came from both of the reactants, but by golly, that's what creates it, gives its concentration. Yep. So if it's okay with you, I'm going to go ahead and piggyback on that 0.0123 moles of NaOH. I'm going to go right to step 2. Earlier we said if you had that, 27.7 milliliters of 0.444 molar NaOH, you have 0.0123 moles of NaOH. I'll put that over 1. And then I'm going to go ahead and use the stoichiometry here. I want moles of NaOH to cancel, be left moles of Na2SO4. So it looks like 1 mole of Na2SO4 on the top over 2 moles of NaOH on the bottom. And then we're done with that part. So looks like we got that same number again, didn't we? Rounding to 3 sig figs, we have 0.00615 moles of Na2SO4, and we're almost done. So we're going to divide that by the total solution volume. But remember, I'm all about showing your work, so don't just plug those 2 volumes in your calculator and come up with a volume to divide those moles by. So here's showing adding the moles of Here's showing adding the volume of H2SO4, which is 25.0 milliliters, plus the volume of NaOH, which is that 27.7 milliliters. So, like Mike was right, the volume that your Na2SO4 is swimming around in is 52.7 milliliters. So now we're ready to go ahead and divide. So we're going to put those moles on the top, 0.00615 moles Na2SO4, and then in the volume we'll put our milliliters, 52.7 milliliters. And we need to introduce one more term to clean up our milliliters, make them cancel, and be left with units of liters. So the second term is 1,000 milliliters over 1 liter. And 3 sig figs, I get a number of 0.117. So what that means is 0.117 moles of Na2SO4 per liter of solution, or simply 0.117 big M, Na2SO4. Okay. Any questions about that? Okay. All right. So these will be due on Friday. Fabulous Friday. Kind of take a look. Is that like a? Oh, it sounded like a 3-wheeler or something running around out there. No? Okay. Motorcycle or what? Can't hear? Okay. Okay. They look like this. So I don't know how many hints you want, but like what you're going to see is I basically take those numbers and put them under the balanced equation. And it's just kind of similar to what we did. Notice we know more about our silver nitrate. We can get moles of silver nitrate from volume and molarity. And then we can use stoichiometry to get to moles of K2CrO4. And then once we have moles, then we can use molarity to get to volume. So that's it. And then the other one looks like this. Now you might be saying, well, what's up with the grams thing? Let's just see. This is a good time to see. So how many grams of calcium hydroxide are required to react with HCl? And the HCl, we know the molarity and the volume. So, of course, from molarity and volume of HCl, we can get to moles. And then from moles, we can get to use stoichiometry to get to moles of calcium hydroxide. So this is kind of a different, this isn't straight aqueous solution stoichiometry, because one of our things is a solid. but it's this kind of a similar approach. Okay, so use volume and molarity to get to moles, use stoichiometry to get moles of the other thing. And then we're kind of back to doing what we did in Unit 1, I think it was Unit 1, where if we know moles, but we want grams, we can use molar mass. Okay, so that's how that one goes. Now the next one kicks it up a notch. Okay, B is basically the same reaction, but we know a few different things. So up there in green is what we know about B. So for B we have volume HCl solution, which is not pure HCl. We have weight percent of HCl. We have weight percent of HCl in the HCl solution, and we have density of the solution. So I can't remember which unit, if it's this unit or the previous unit, but you can use those three pieces of information, and the molar mass of HCl, to get to moles. Bottom line, what it says in purple is kind of what you did before, where you have to use weight percent, density, what else we got? Volume, and molar mass to get to moles. Once you have moles, then it's like the other one. So we get moles of our HCl. We can use stoichiometry to get to moles of the calcium hydroxide. Once we know moles of a calcium hydroxide, we can get to grams of calcium hydroxide using the molar mass. Okay? All right, next one. It's a gram one again. Not grant, gram. Okay? So in this case, notice that we know the mass of the solid, oxalic acid. Okay? And I always tell you to look to see where you can start, okay? Notice that the solution, we have a question mark there. But we have the mass of the solid. We can use the mass of the solid, the molar mass of the solid to get to moles. And then we can use stoichiometry to get to the moles of the other thing. And once we have the moles of the other thing, we can use the moles and the volume to get to molarity. That's it. It's like a little puzzle. Okay, and last but not least, we have this one. Oh, this one's good. Okay, we have the chemical reaction of interest is the first one, and we kind of a cleanup reaction following it. So notice that we have excess HCl. So if we call this equation 1 and equation 2, which is I'm going to do in a minute, we're going to have HCl carry over and do this equation B. Okay. So for equation B then, we go ahead and take our excess HCl that didn't react with our CaCO3, calcium carbonate, and we react it with barium hydroxide. Now what we do know is enough information about the barium hydroxide to get moles. We have volume and molarity. So here's how this looks. Your question is, how concentrated is that HCl solution that you're using? So I would start here to get the moles of barium hydroxide, and then use stoichiometry to get the moles of HCl. And then once you have those, then I would set that aside. I would use the mass of calcium hydroxide to get to, and its molar mass to get to moles. And then get to the moles of HCl. So at that point, you have moles that were left over that reacted with your barium hydroxide. You have moles that reacted of HCl that reacted initially with your calcium hydroxide, so you have 2 moles. And we have an overall volume that you started with of 25 milliliters. So that's it. That's how I would do it. All right? Okay, those are your hints. All right. So a minute ago, when we had the 25 milliliters H2SO4 and we added 27.7 milliliters of NaOH, that actually was a titration. The pipettes that you guys are using, you guys have been using 10 milliliter pipettes, 10.00 milliliter aliquots. Well, there's an awesome pipette that's a 25.00 milliliter transfer, okay? So in a titration, basically, you have two reactants, just like our H2SO4 and our NaOH, that we want to get together to go to form products, okay? And if they both dissolve, then they work well with this titration. Now, the thing that you're going to drip in is placed in a piece of glassware called a burette. Burettes are great for a number of reasons. Burettes have gradations on them that are pretty tight, okay? And burettes then have what's called a stopcock down here. Can you see that kind of dark thing? Okay, that actually, this thing turns, okay? So that it turns to, right now, by the way, it's wide open. So this would be like letting all of the liquid come out. So if it's a 90-degree angle, it's all the way off. If it's parallel, it's all the way open.
It's a shut-off valve.
It is a shut-off valve, totally, exactly. So that is our burette. What's in the burette, and the word is coming up, is called the titrant. So like the liquid in here. Oops. There's liquid in here. That liquid is called the titrant. Yep, exactly. And we use our shut-off valve to open and close it to let liquid come out. And in the case of the example we looked at, and actually in what you guys are going to be doing tomorrow, the titrant is going to be sodium hydroxide. A lot of times it's the base. Okay, so the titrant is what's in the burette. So there's two solutions aqueous solutions that are going to be admitted together. What's waiting underneath the burette, actually, and yours is going to be in a Erlenmeyer flask, which kind of works well, is what we call the analyte. So in the example we looked at, the analyte was the H2SO4, the 25.00 milliliter aliquot of H2SO4. And for you guys tomorrow, it's going to be HCl. And I can't remember if this is also vinegar or not. So the analyte's what's waiting. So those are your two reactants. And this isn't working. I tried it today. But here's some still images. Now this right here, I told you guys you're using an E-flask and an Erlenmeyer flask. That's what you guys are going to use tomorrow. It works great because stuff doesn't come flying out of it very easily. An important step being shown right here is to add a visual indicator. And I've definitely done my fair share of titrations and forgot to add the indicator. If you don't add an indicator, it's not going to show you what we call your endpoint. So you guys are using phenolphthalein that smells wonderful there tomorrow. So you can see the tip of the burette and kind of the orange stopcock. There it looks like it's partly, can't be totally parallel. Okay, so it's a little bit closed, and you see a drip of your titrant coming into your analyte. Actually, the experiment you're going to be doing, I mentioned you're using phenolphthalein indicator. It will turn on, if you tell this is a slight pink. Okay, that means that you have dripped in just the right amount to use up all of your analyte. You've added just the right volume of titrant with that given molarity to use up all of the other reactant that's there as an analyte. It's wonderful. So what works well as a titration? Well, you need to be able to dissolve them. Okay, it needs to be able to be juiced up, and usually the solvent of choice is water. So you need to be able to get both reactants in solution. One will be your titrant and one will be your analyte. One's in your burette and one's waiting underneath there. And then to do any sort of calculations, you need to know the reaction behind what happens when your titrant and your analyte meet. You need to know the chemical reaction. Specifically, you need to know the balanced chemical equation. The reaction has to be fast. So I mentioned dripped in. So basically from your burette, you drip in some titrant. Can you imagine if there's like even a 10-second delay? We're going to get impatient for one thing. Okay, but if it takes about 10 seconds for your titrant to react with your analyte, that delay, if you're not aware of it, could really throw you off. Okay, so it needs to be fast. And it needs to go to completion. In other words, there needs to be a true endpoint in which all of your analyte, the stuff in your Erlenmeyer flask, has been used up by stuff that you dripped, by your titrant. We talked about reasons that you don't get 100% yield, and one of them is these chemical equilibria, okay? So basically, your reactants proceed to products, and then your products, some of them, to a certain extent, proceed back to reactants. It doesn't go to completion. And I mentioned don't forget to add your indicator. Okay. Now, there's actually two broad ways of telling that you have, being able to determine that you have used up all your analyte with your titrant. One of them is by adding something that's colorful, that we're going to use tomorrow, phenolphthalein. Changes its from clear to pink when basically you have reached that tipping point. And the other one is potentiometric, which just simply means kind of seeing what sort of current that solution will conduct, is driven by what sort of species you have running around in there. So the tipping point, the equivalence point, is the point at which you have used up all of your analyte by dripping in your titrant. In other words, at your equivalence point, if you drip in a little more titrant, you'll have excess titrant, okay? Before the equivalence point, you had excess analyte. So it's right at that tipping point. So we have equivalence point and end point. It's funny because I've seen kind of shorthand we call, I'll say equivalence point EP, like a lowercase e. Okay, like this. Equivalence point is EP for equivalence point, but that could also stand for endpoint. Now, endpoint should be your equivalence point, but endpoint is when the investigator says, we're done. We have added the right amount, the right volume of titrant. And equivalence point is when it really happened. So the more that those match up, the better you're at. Okay. So tomorrow, I just know that I'm going to hear some, I just went past it.
Equivalence would be like the theoretical endpoint would be
right.
The experimental.
Yes. Josh said equivalence point is like the theoretical, and endpoint is like the experimental. I buy that. So endpoint, experimental, and this is theoretical. I think that works. So hopefully they're the same. If I don't, I'm gonna run through titrations tomorrow, and if I forget to tell you this, sometimes what people will do is if they think they're at the right place for their endpoint, they will go ahead and record the volume on your burette, okay, and then they'll add one more drop, and then if it's a better one, then they'll go with that with the drop added. But if it looks like they over titrated, then they'll go to the volume before. So it's a thought. It's a little game we play. So something like phenolphthalein is a visual indicator. Alternatively, you can actually, and I did a little bit of this work as an undergrad kind of research. Alternatively, if you have kind of a wafer of where you have electrodes and you're measuring the resistivity of that solution, okay, as during the titration, the conductivity, resistivity of your solution changes. So that's another way to kind of track to see what's going on. Okay. So let's do a problem, shall we? This CH3COOH is acetic acid, CH3COOH. And of course, NaOH is sodium hydroxide. And if you read it, let's see, is this where I want to? Yeah, let me go ahead and just kind of write information under the balanced equation. So we have 50 milliliters. That's a big pipette, let me tell you. We've got one in the lab, but we have 50 milliliters of your acetic acid. Okay. And the molarity of the NaOH is known, and that's 0.1150 molar. Okay. What else do we know? All right. So down here it says that, well, let me start that this. The burettes are actually, the top mark is 0. And the burettes you're using are 50 milliliter burettes tomorrow. So, if this is your burette, here is your stopcock right here. This mark up here is 0 milliliters. We have 10, 20, 30, 40, 50. So what this is saying is they started with an initial burette reading of 0.048 milliliters. They said they went ahead, and this is where, this, by the way, is the NaOH. That's the titrant, and in here is the acetic acid, CH3COOH. And specifically, this is 50.0 milliliters. So they added phenolphthalein, so they didn't forget their indicator. And they dripped this into here until they got that pink. And once they dripped the right amount, their final burette reading was 23.90 milliliters. So how can they get the amount dispensed? This is the initial, this is the final.
Subtracted.
Simple subtraction, exactly. I mention that because actually, do you see, and that's the titrate, that's the NaOH. So under here, actually I can say volume is equal to, I'll go ahead and write it down, 23.90 milliliters minus 0.48 milliliters. Okay, now since I've done that, and I'll put question mark molarity for the CH3COOH. Does that kind of look like what we've been doing? We have molarity and volume of NaOH. We have volume of CH3COOH, and we're after molarity. Totally exactly what we've been doing. So let's see how the calculations go. Okay, so our analyte is what is being dripped into. Analyte. Our titrant is what's in the burette. Okay, so you told me I could get to the volume of titrant, the volume of NaOH, by subtracting. So don't forget, since we're subtracting, we don't round according to significant figures, it's according to decimals. So if you take 23.90 minus 0.48, you get 23.42 milliliters. Okay, so we're going to use that volume and the molarity to get to moles of NaOH. So it's like what we did before. If I start with that 23.42 milliliters over 1, and this is the moles of NaOH. And then I convert that to liters by going 1 liter over 1,000 milliliters. And then I introduce the molarity term. I want liters to cancel, so I'm going to use the unflipped version of molarity. So if I go 0.1150 moles NaOH over 1 liter, then milliliters cancel, liters cancel, and we're left with units of moles, which is awesome. I get 4 significant figures. So 0.002693 moles of NaOH. So like we did before, now we're going to go use stoichiometry to go from moles of NaOH to moles of CH3COOH. And they have a 1-to-1 relationship, so it simply looks like this. 0.002693 moles NaOH times 1 mole CH3COOH over 1 mole NaOH. It's not sufficient just to say it's 0.002693 moles of CH3COOH. And you might be, well, why not, Mrs. Snipes? Because it is. And, well, a few reasons. One is about communication. How did you get from point A to point B? And another is it's not a good habit to get into because you don't know what the next stoichiometry, it could be 2 to 7, relationship. Okay, so now we have moles and we just have to divide by that aliquot volume, right? Our 50 milliliters. So if we take that moles, 0.00263 moles of CH3COOH divided by our 50.00 milliliters. This is where, to me, it's hard to work this sort of problem if I don't do one of two things. I either have to have a picture where I show the NaOH dripping into the CH3COOH, or I have to go ahead and write it under the balanced equation. If I don't, I'm lost. I'm totally lost. Okay, so that will give you moles per milliliter, and then we need to introduce a term to convert milliliters to liters in the denominator. So 1,000 milliliters over 1 liter. Now we have moles per liter, which is great. We're still allowed 4 significant figures. So I got a value with 4 sig figs of 0.05387. And then units would be moles of CH3COOH over 1 liter, or simply a capital M, which is molarity. What do you think? It's a titration experiment, titration calculation. Okay. So I have one more problem, and in order to do this problem, in order for this problem to make sense, I need to introduce this idea of spectator ions and net ionic equation. Why? I don't know why, just to complicate things. But we talked, actually, this is a deja vu slide, because we talked about if you have an ionic substance, solid, and you dissolve it in water, it's going to break apart and it actually will conduct electricity, okay, give you an electrolyte. So for instance, sodium chloride is an ionic compound. It's very soluble in water. It breaks apart to give you, and we'll be talking more about cations and anions, Na plus and Cl minus. Calcium nitrate gives you 1 part calcium, 2 parts NO3. Kind of like you guys did for your homework that's due today. And we did this one. Just intuitively, if we have a calcium nitrate solution that's known to be 0.230 molar, the fact that it gives me 2 parts of NO3 means that the molarity of the NO3 is going to be twice the 0.230 or 0.460 molar. We did a problem like that yesterday, or you know what I mean, Monday. Well, I want to introduce something else now called a net ionic equation. This is one of those definitions where it has something that I need to define in the definition. I need to further define it on the next slide, but it's in this definition. You know what a chemical equation is. It describes a chemical reaction. It can be balanced or unbalanced, right? Well, in a net ionic equation, you have removed the spectator ions. Well, you're like, well, what's a spectator ion? Well, a spectator ion, just like a spectator watching a sporting event, a spectator is one that doesn't get involved. It's just there to watch what's happening. So there are these ions that are just running around in solution, just watching the chemical reaction occur. Those are spectator ions. How do you know it's a spectator ion? Well, if I have a reaction arrow between my two hands, if you see the ion over here in the same form as you see the ion over here, if they could be deleted, okay, they're the same to begin with, the same to end with, they're not involved in the chemical reaction. Those are spectator ions. And they actually can be removed and create what we call a net ionic equation. That's it. All right? So, we're going to apply that idea with this last problem. A lot of words here, okay? And I have the equation coming up here in a minute. I printed it off to bring, but I didn't bring it today. So it's a titration. We have a solid that is your analyte, and we are dripping in KMnO4. Also in your analyte, we have H2SO4. Okay. So in your burette, in your titrant, the KMnO4 stands for potassium permanganate. Okay, breaks apart to give you Ks and MnO4s, specifically K plus 1, MnO4 minus 1. Your sulfuric acid that was in with your oxalic acid breaks apart, one hydrogen kicks off, and it gives you H or H plus and HSO4. So here in a minute, or I should say, when that chemical reaction does its thing, the only thing we care about in the KMnO4 is the MnO4. The only thing we care about in the H2SO4 is the H. So in other words, your K plus, we don't care. That's a spectator ion. Your HSO4, which is the bisulfate polyatomic anion, HSO4, we don't care. So K plus and HSO4 are just along for the ride. So when you remove your K pluses, and you remove your HSO4 minuses, this is what you end up with. See, I wish I was doing it on a piece of paper instead of the PowerPoint, but just let me go ahead and jot this down so that we can write a few things underneath it. This, we need 5 moles. This is your oxalic acid, H2C2O4. That's a solid. And it is going to react with 2 moles of MnO4 that you're dripping in. And it's going to need 6 moles of your H plus that you got from your sulfuric acid to form a whopping 10 CO2s, gases. And also being produced is Mn plus 2 and 8 waters. Whew, good heavens. So let's go back again and look at the information from the problem. I have a mass now, that 0.2585, to go right under this guy right here. That's my oxalic acid. My 22.35 milliliters is actually going to now, I'm going to put it under my MnO4 because that came from KMnO4. So we have 22.35 milliliters of KMnO4. And the molarity of, oh yeah, question mark, big M. There we go. Now, oops, my bad, units. Now, hopefully this looks familiar as homework that we've already talked about that's going to be due, I guess, on Friday. Do you see where we have grams of that solid that we can get to moles using the molar mass? Does that make sense? Okay. And then from that, we can get to moles of KMNO4 using stoichiometry. Oh, sorry. Moles of MNO4 using stoichiometry. It's got this cool 2 to 5 thing, which we haven't seen a lot of. Okay. And then once we have those moles, we're after molarity of KMNO4. Once we have those moles, we can link, kind of have an extra step here, link our MNO4 with your KMNO4, which is a 1-to-1. Remember I kind of showed you with the net ionic equation. And that will get your moles of KMNO4. And we're almost there. And then once we have moles, we can use the volume to get to molarity. So here we go.
I have a question.
Yes?
How do we know that the potassium and the HSO4 are
I'm just telling you this time, yeah.
That would be given?
Yeah, that would be given. And I won't ask you to identify at this point and remove them.
Okay.
Yeah. And when we, in Chem 2, talk about spectator ions, it would be more obvious.
Okay.
Yeah, and this time it's just an example I wanted to give, and I had to explain why I ended up in this form.
Cool.
Yep. So I was bad here. I didn't show you where the 90.04 grams per mole came from. My bad. Don't do as I do, do as I say. So you need to show me a molar mass of H2C2O4, and you would come up with 90.04. Okay. Rounding to 4 sig figs, the moles of H2, oh, sorry, looks like I'm going all the way. Usually I would stop there, but I'm actually combining step 1 and step 2 if that works for you. So unit-wise, that gives you moles of H2C2O4. If I want to now go to moles of MNO4, I use stoichiometry. So I have 2 moles of MNO4 over 5 moles of H2C2O4. And I'm actually going to combine the third step here. So if you're okay with that, you'll see unit-wise, that has left me with moles of MNO4 minus. So of course, I can now put 1 mole of KMNO4 over 1 mole of MNO4 minus, gives me units of MNO4. Excuse me, gives me units of KMNO4. So when the dust finally settles, we're allowed 4 significant figures. That's the moles of KMNO4. I can go ahead and divide by that volume. 0.001148 moles KMNO4. Almost done. So I take those moles and divide it by the volume of solution. It looks like this. 0.001148 moles, or moles KMNO4, divided by 22.35 milliliters. We need to go ahead and get liters in the denominator instead of milliliters, so introduce a term 1,000 milliliters over 1 liter. Round to 4 significant figures. Looks like this. We get a value with 4 sig figs of 0.05138, and units would be moles KMNO4 per liter of solution, or simply the capital M for molarity, KMNO4. I know I went a little over this time. Not on purpose, I assure you. Okay, so I know it has 550 struck out, but yes, 550 is also due. So these 3 will all be due. And I have hints. Anybody who wants to see the hints? Who wants to go ahead and go? So if you want to go ahead and go, go. And if you want to see the hints, they're coming up momentarily.
Will they be on Twitter?
Yeah.
Okay.
So you don't want to see the hints either?
These will be
Who's,
clear.
do you still want to see the hints? Or you just want to? Peer pressure. Okay.
So are we gonna have like a
You could have a very similar problem where you're given the grams of the solid analyte and you're given the volume of the titrant and asked to find molarity. But it wouldn't be like this, where it's kind of going from removing a spectator ion in the equation. So if that's your question, it won't be like that, but it could be, like I said, grams to finding molarity.
Yeah,
So like-
definitely, I'll get your number.
Yeah.
Okay, cool.
Yeah.
Kind
Yeah.
of, so I was like,
Hmm.